in my system, maybe because of that, the things are becoming very slow. I have restarted this thing. Let me see how it works. Now, I will continue. I shall continue from where I left in the last class.
Okay, sir.
Now, in our last class, we had been discussing different mechanisms or modes of heat transfer. That how in different ways heat can flow from a body at a higher temperature to a body or a region at a lower temperature. Now it can happen through three different modes. We have already discussed about the conduction mode, and it is that when the molecules or the particles they occupy their mean position, but still they vibrate about their mean position, and when they come in contact with each other, the particles, they convey the heat to the next layer where the temperature is low. In in contrast to that, in the convection mode, there is a physical movement of the particles, energized particles, from a zone at a higher temperature to a zone at a lower temperature, and it is conveyed through motion of the fluid, and that is shown in with some kind of comparison with figure or mode 3 in this figure, when the person is carrying the water from the source to the destination point, and convection heat transfer happens like this. Then there is third mode. There is a radiation by which you can have heat transfer from a heated zone to a colder zone, where the intervening medium may not have much role to play. Even if there is no intervening medium, the heat can be transported by conduction from one surface at a higher temperature to a surrounding surface at a lower temperature. For that, there is no need for a conveying medium that is required otherwise in conduction and convection. We require to have a conveying medium. The medium may remain more or less static at its own position, or it may move from one position to another position. But in the case of radiation, no such need is there to have a medium in between. If there may be a medium, and the medium may participate, may not participate. If the medium is a so-called clear one, then the intervening medium may not participate into this heat transport process by radiation. By clear I mean that when the radiation passes through that medium, it does not get absorbed, reflected, refracted. Those type of things do not happen. On the other hand, there may be medium radiation passes through space. It may strike on a particulate medium, and some of the energy of the radiating heat transfer may get present radiation. Radiation. Yes. That rate of heat transfer. Again, let me repeat that in this subject, whenever we talk of heat transfer, we mean mostly it is the rate of heat transfer. We may not utter the term rate of heat transfer, but mostly in this subject, we talk about heat transfer rate, even though the rate term we may not use at many times. Now, if we want to find out what is the rate of heat transfer in a given situation, then we have to go through certain quantified approach, that what is the magnitude of the rate of heat transfer that takes place in a given situation. Now, to do that thing, the first thing we should do is to identify the mechanism by which the heat transfer is taking place. The first thing that we should do is to try to identify the mechanism of heat transfer. Because once we identify the mechanism of heat transfer, then only we'll be able to apply the appropriate laws that govern that mode of heat transfer. So first what we'll do is that we'll try to identify the mechanism, and then we'll try to apply the appropriate form of governing laws that dictate the rate of heat transfer through that mechanism. For example, when we talk of conduction heat transfer, then we know that the conduction heat transfer from one surface to another surface. Suppose this is a body. This body may represent one wall of a room. Suppose this represents a cross-sectional view of a wall of a room, and this is one wall that is exterior to the room, and this wall, this surface may represent the inner surface of the room. This is a wall, this is a wall, this represents the surface external to the room, external to the house, so that it may be exposed to maybe incoming sun rays, solar rays, and this outer surface may be heated. On the other hand, this surface, it represents the inner surface of the wall that is in contact with the air inside a room. Now, it is normally expected that if this is an exterior wall of a house, then this exterior wall may have an incoming solar radiation from outside, and naturally this surface will be heated, means it will be heated in comparison to this surface, which is the inner surface. So there is a difference in temperature across this thickness of the wall. Now, this is at a higher temperature, this surface is at a lower temperature, so we can expect that the heat will flow from higher temperature to lower temperature across the through the thickness of the wall, and the mechanism of heat transfer here is a conduction mechanism, because the medium cannot move, so there cannot be any convection, and if it is a non-transparent opaque surface, then there cannot be any radiation. So the only way heat can travel from a higher temperature surface to a lower temperature surface will be by means of conduction. So what we will try to do is to apply the appropriate laws of conduction. We'll come back to these figures later on. Now, you know that this phenomenon of heat conduction will be governed by a law known as the Fourier's law of heat conduction, where we can find out the heat flux due to conduction as equal to minus k into dT dx. Now, I have a lot of things to say about this thing. First of all, what is heat flux? Now, when we talk of the heat transfer subject, although we are interested to find out the heat transfer from an entire wall, when we want to find out the heat transfer across this wall, then we require to know what is the rate of heat transfer across this wall. Mostly what we will do is that, to do that thing, we will try to find out what is the heat transfer rate per unit area. Even though our interest is to find out the rate of heat transfer through the entire surface, but to do that thing, sometimes it will be necessary to find out the rate of heat transfer per unit area of the surface. And once we find out the rate of heat transfer per unit area of the surface, then we can, to find out the rate of heat transfer through the entire surface, we can integrate that thing. The earlier thing is the rate of heat transfer per unit area that is known as the heat flux. So if we integrate the heat flux over the entire surface, we get the heat transfer rate from the entire surface. Now this integration may be simply equal to the heat flux multiplied by the surface area if the heat flux is uniform over the entire surface area. If the heat flux is uniform over the entire surface area, then the heat transfer rate will be simply equal to the product of the heat flux, which may be constant over the surface, into the total surface area. On the other hand, if the heat flux varies over the surface area, then we cannot get the heat transfer rate by that approach. Then what we have to do is to integrate this heat flux over the surface area of interest. So mostly what we will talk about initially is about the heat flux. The heat flux is known as the rate of heat transfer per unit area or heat transfer per unit time per unit area. And because it will be per unit area, so it has a dimension of energy per length square. So to indicate that length square, these two primes are indicated. That is, it is per unit length, something like that. So this Q double prime will indicate the heat flux. And to find out this heat flux, normally we take help of, if it is not known, then you have to take help of the Fourier's law of heat conduction. This Q, there are different books, they use different symbols at different places. So there is no standardization, and also we should try to be uniform in our use of the symbols, but sometimes we may commit some error, so we may make that mistake, and one such mistake is this, that as I said, heat flux can be shown either by Q double prime. Sometimes also the heat flux is shown with the help of simply Q, lowercase q. This lowercase q or small letter q also indicates the heat flux. Whereas when we talk of the rate of heat transfer, we will indicate this with the help of q dot. On top of a capital Q, we will use a dot quantity to indicate the rate of heat transfer. The heat transfer rate is indicated by capital Q dot, whereas the heat flux will be indicated by either small q or q double prime. Small q double prime or small q. That indicates the heat flux. And this heat flux, what is the unit of this thing? It will be the rate of heat transfer per unit area. So the unit will be watt per meter square. Now, this heat flux is proposed by Fourier in the form that the heat flux across a surface will be given by or will be proportional to the temperature gradient. So the temperature gradient is shown as dTdx over here, and the heat flow will be taking place in the direction where there is a negative temperature gradient. The heat will flow only in the direction of negative temperature gradient. So dTdx will be always negative in the direction along which the heat flows. So because this is a negative, so if you want to find out the magnitude in a positive sense, then there will be a prefixing of a negative sign so that this negative and this negative cancels each other and we get the magnitude in a positive direction. So in the direction of heat flow, the magnitude of the heat flux will be given by minus K into dTdx. This K is a property of the material. That property of the material is normally symbolized as small k, and it is known as the thermal conductivity of the material. Now, if you see this thing, the heat flux that is dependent on two things simultaneously. One, it depends on the property of a material, a specific property of a material, and also it depends on the situation that is prevalent on the body. Now, this is something that is not intrinsic to the material. This property K is specific for that material. If we change the material, then naturally the conductivity value will change from one material to another material. So this is something that is dependent on the material exclusively, and this is something that is independent of the material. This is something that has been created because of external things, like when the sun rays that fall on a surface, it establishes certain temperature gradient. So this thing is not controlled by the material, rather it is created by the external situation. So heat flux depends on two things simultaneously. One, a material property, another, a situation created by external things. Not only it is created by external thing, some part of that is also dependent on the geometry of the body. So three things are involved. One, a material property, that depends purely on the type of material that you are discussing. It also depends in a sense about the geometric feature of the body, whether the wall is a thicker one or a thinner one. That will dictate the temperature gradient, and also something external to the body, something external to the property of the body, something external to the geometry of the body. Then another thing that determines the rate of heat transfer. That is the external disturbance created due to incoming energy from the solar rays. So all these things together dictate what will be the rate of heat transfer across a wall, also what will be the heat flux across a wall. Another thing that I would like to tell is that in this situation, it is assuming that the heat is flowing only along the x direction. What is the x direction? If we think of this direction as the x direction, here we are assuming the heat is flowing only along the x direction. And when we can make this type of assumption is that the heat is flowing only along one direction is when the thickness along that direction is very small compared to the length dimension in the two other direction. That is, this wall has an area constituted by some height and some depth. Now, if the height of the wall and the depth of the wall they are much larger than the thickness of the wall, then the whole gradient, the major amount of temperature gradient, will be along the thickness direction, which is the smaller direction. Because this being a thinner dimension, the resistance to heat flow will be very small over this direction. The heat flow, that is something similar to your Ohm's law, where the flow is equal to a potential difference divided by a resistance. Here also, a similar approach we can adopt, that the flow of energy known as heat energy that can be given by the ratio of the potential difference for heat flow, that is the temperature difference. Heat flows because of a cause, that is the temperature difference. So that we can call it as the potential difference is equal to the rate of heat flow will be equal to temperature difference by a thermal resistance. Now that thermal resistance will be proportional to the thickness along which the heat is flowing, and it will be inversely proportional to the cross-sectional area through which the heat is flowing. Now, here what we see is that the thickness, if it is small, then the resistance should be small because of the thickness is proportional to the resistance is proportional to thickness. Also, the resistance is inversely proportional to the area of cross-section. And if you see the area of cross-section in this particular direction, that is given by the height of the wall multiplied by the depth of the wall. So what will happen is that the thickness being small and the area of cross-section being large, the resistance along this direction will be very small compared to the resistance along y and along z. If you call this direction as x, and if you call the height direction as y, the depth direction as z, then the resistance along x is much smaller compared to the resistance along y and resistance along z. As a result, majority of heat will flow along the x direction. So what we'll see is that we can say it in a different word, that the heat flow along x should be considerably large, and heat flow along y and along z, it will be negligibly small. So when things are negligibly small, we can assume them as equal to 0. We can assign a value of 0 to them because those quantities will be very small, they will be negligible, they will be insignificant. We can neglect their magnitude and we can say the heat flow along y is 0. We can say heat flow along z is 0 and there is only significant amount of heat flow along x, that is across the thickness of the wall. So if heat is to flow along x direction, that also implies another thing is that there is significant temperature gradient along x direction. And because heat flow along y is 0, that also implies that the temperature gradient along y is also negligible. And when we talk of heat flow along z is 0, that also means that temperature gradient along z is also negligible. So this is an example of a one-dimensional heat flow. Here the heat flow is not multi-dimensional, but it flows only along one dimension, that we can call it as x direction. So when heat flow takes place along one direction, that means the temperature varies only along that direction. So here is an example where you can assume that temperature varies only along x. So the temperature gradient along x can be shown by an ordinary differential. That is
Sir, in
why.
these cases, we have considered the temperature to be constant with respect to time, right? Or is it varying?
Can you be a bit louder, please?
Sir, I'm telling that in the above cases, we have
Just
considered
one
the
minute.
temperature.
Just 1 minute. Let me increase the volume of my speaker. Please repeat.
Sir, now can you hear me?
Yes, yes. No.
Yes, sir, I'm telling that in the above three cases, we have considered that temperature is constant with time, or the temperature is varying with the time also.
We have considered. I try to tell things in a gradual way because there is a lot of things to be covered. First, we try to discuss about the temperature variation along in the space. So what we talked about is that temperature is a function of x only, is not a function of y and z. Apart from this, there is another thing that we can consider that the whole phenomenon can also vary with time. Now, when we discuss something that is where the phenomenon is varying with time, then it is called an unsteady state phenomenon or transient phenomenon. And when the phenomenon is not changing with time, then we call it as a steady state phenomenon. What we are discussing here is a phenomenon that is a steady state phenomenon where T is not varying with the temperature, capital T is not varying with time. Whereas there may be cases where temperature can also vary with time. In general, this capital T can be a function of x, y, z, and time. That is the most general thing to happen. Now, most of the time, we'll see that if we consider the general thing, then it leads to a complicated situation to tackle. Now, when the need arises, we must take the complicated situation. But many times we'll see that whether we take the complicated situation into consideration and arrive at a result, and when we simplify this thing appropriately, may get another result, and that this result, that is the complicated the phenomenon taking into consideration all the things into consideration and a simplified approach, the results may not vary much at times. Then it will be prudent or wiser to take a simplified approach. Now, when we take the simplified approach and when we cannot take the simplified approach, that is a matter of judgment and expertise. But that also is very important. Just to make things simplified, we should not simplify. We should keep this in mind that it should not lead to an erroneous result. But if the results are satisfactory for the purpose for which we are calculating by taking simplified approach, then it will be better to go through a simplified approach. And even then, we may see in cases the results are accurate enough. But there will be cases where if we adopt a simplified approach, there the results will be highly erroneous. In that case, obviously we will not take a simplified approach. We have to take all the complexities into consideration. But
Obviously.
what we are discussing is a case because we are beginning this course. We are going through we are just trying to introduce a very simplified thing, that is we have a heat flow that is occurring only along X and it is not occurring along Y because of the high resistance along Y. It is not occurring along Z because of the high resistance along Z, and also it is not changing with time because the situation, the surrounding situation is not changing with time. But if you see this, the what I try to tell is an example where the heat transfer is because of the incident ray coming or falling on the outer surface of a wall. Now, this type of phenomenon, it will not change drastically or rapidly. Whatever change will occur, that will change very slowly. So, if we take a very small window of time, within that small window of time, the thing can be taken as a steady state phenomenon, and within that small window of time, nothing may vary much drastically. The temperature will not change drastically, so we can take the situation as a steady state one. But if we want to study the whole day phenomenon, then we are quite aware that the temperature will change drastically over day and night. In that case, we have to take the time-wise variation of the phenomenon also. And then if you want to find out the heat transfer rate, it will be obviously a time dependent thing, and if you want to calculate the heat transfer rate for the entire day, then not only you have to integrate over the surface area, you also have to integrate over the time period of interest. Now, coming back to your question, which is a very good and pertinent one, that what we are discussing is a phenomenon that is a steady state phenomenon. Okay. In that case, the time-wise variation is not taken into consideration. Not only that, we are not taking into consideration time-wise variation. Also, we are not taking into consideration temperature variation along Y and Z. We are taking a case where temperature is varying only along X. And because it is varying only along X, that is why the temperature gradient along X is taken as dTdx. But if we have a situation where the temperature varies not only along X, but also it varies along Y, then naturally the temperature gradient along X cannot be taken as dTdx. Then we
We
have
have
to
to go with dot T.
then we have to take a partial derivative of temperature along X, that will be del T del X. If we want to find out the heat transfer rate, the heat flux along X, then we should indicate that as equal to Q suffix X equal to minus K into del T del X. Similarly, if we want to find out the heat flux along Y, we have to indicate that as Q suffix Y equal to minus K into del T del Y. Because in that example, we assume that because it is realistic that T is varying along X and Y, yet it may not vary along Z, it may not vary along time. If we have a case of a three-dimensional steady state heat transfer, then it implies that steady state means T is not changing with time, but if it is three-dimensional, means heat flow is taking place along three dimension, then you have to find out Qx equal to minus K into del T del X. Heat flux along Y, Qy will be equal to minus K into del T del Y. Heat flux along Z will be Qz equal to minus K into del T del Z. But there will be no change of heat flux along time, maybe. And the most general case may be where we have everything is changing along X, the T is changing along X, Y, Z, and time. Then also it will be obeying the same Fourier's law that Qx will be equal to minus K del T del X, Qy will be equal to minus K del T del Y, Qz will be equal to minus K into del T del Z. Now, one more thing that is important over here is that this property, the conductivity, we assume we are so far we are talking of a conductivity value that is the same irrespective of the direction. There may be cases where the conductivity also can change along with the direction. The conductivity in a particular direction may be some value, and the conductivity in another direction may be of another value. So the conductivity property also may be direction dependent. Then we call it as an anisotropic material where we have to take Qx equal to minus Kx into delta del x, Qy will be equal to minus Ky, Ky means K suffix y into delta del y, and Qz will be equal to minus K suffix z into delta del z. Those are cases which are for anisotropic material. So when we deal with a situation, we also have to know what is the character of that particular material, whether it is an isotropic material or an anisotropic material. So accordingly, we have to check the appropriate values of our conductivity of the material. Okay. Now coming back to this thing, the property conductivity, be it isotropic or anisotropic, what will be the unit of that thing? That will be equal to the unit of heat flux divided by the unit of temperature gradient. Now the K value that is equal to, that will have a unit of watt per meter square, that is the unit of heat flux, watt per meter square divided by Kelvin per meter or degree centigrade per meter. So this meter square and this per meter, it will cancel 1 meter. So the unit of K will be equal to watt per meter Kelvin or watt per meter degree centigrade, something like that. So the unit of that K, it will be in SI system maybe watt per meter Kelvin or joule per second meter Kelvin, or it may be watt per meter degree centigrade. Now there is a common mistake sometimes we commit is that if we if we are interested to know the conductivity value in watt per meter degree centigrade from watt per meter Kelvin, the value will be the same, because what is happening during this thing, whether we take this temperature in Kelvin, the absolute scale, or degree centigrade, what we are taking is the difference, because to find out the gradient we have to take a temperature difference divided by the geometric difference. Now, so when we take the temperature difference, the difference will be the same whether the temperatures are individually taken at Kelvin or degree centigrade. So here this K represents the temperature difference in Kelvin. Temperature difference in Kelvin and temperature difference in degree centigrade, they will be the same. If there is a temperature difference of 2 degrees centigrade, then Kelvin wise also it will be a temperature difference of 2 Kelvin. So the unit of conductivity will not change whether we take it in watt per meter Kelvin or watt per degree centigrade. And it is a matter of practice that when we think of this thing, if you are asked about the unit of this thing, you should be able to memorize this thing, or if momentarily even if you forget, you can derive the unit of this thing by dividing the unit of heat flux by the unit of temperature gradient, and then it will evolve out as watt per meter square per Kelvin per meter. It will be watt per meter Kelvin. Another thing that we'd like to tell is that this is something that is denoted as a vector quantity, because this heat flux, if you see this picture, this has a direction. What is the direction of that heat flow, heat flux? That is normal to the surface. So the direction of this will be equal to the direction of the surface. Surface also is a vector quantity that has some magnitude and some direction. What do we mean by the direction of the surface? That is, what is the normal to the surface, what is the direction of the normal to the surface. The direction of the normal to the surface is the direction of that surface. So surface also is a vector quantity, just like that. The heat flux also is a vector quantity. It has a direction which should be normal to the surface. Now, if the surface is inclined along x and y both simultaneously, it will have two components, ax and ay, and heat flux also will have two components, qx and qy. And when we find out the heat transfer rate, what we do is that we make an inner or dot product of the heat flux into the area, where the heat flux is also a vector area is also a vector, and when you make a dot product of these two, you get a scalar quantity known as the heat transfer flow through this surface. Now, that is up to the conduction part. We'll go more into detail, and that's why it is shown as heat flux as a vector quantity by this arrow overhead that is equal to minus k get t. So this heat flux will have I qx plus j qy plus k qj, where ijk are the unit vectors along xyz, and that is given by minus k I del t del x I del t del y I del t del z. And that is considering the conduction part. Now, when we come to the convection part, what we try to do is to find out the heat flux from the surface. In the case of convection from a surface, suppose there is a surface. The surface temperature is given as Ts, and over this surface, a fluid is moving which has a temperature somewhat away from the surface, which has a temperature of T infinity. Now, this T infinity is so designated because the temperature that we are talking about is at a distance that is sufficiently away from this, far away from this heated surface. We have a heated surface at Ts, and if comparatively colder fluid is moving over this surface, and if we come very close to this surface, even inside the fluid, you can sense the hotness of this surface. So if you come closer to this surface, you can feel more and more hotter, and as you move away from this surface, you get the temperature more and more colder. And at a distance sufficiently away, you see that we cannot feel the presence of this hot surface. There, we no more sense the hotness of this hot surface. There we get a uniform temperature that is known as the free stream temperature. Now this T ambient, this T infinity is also called as the free stream temperature. That is the stream temperature far away. That we call it as the free stream temperature, and the temperature of the stream closer to this will be different from the free stream temperature. And at a sufficiently away distance, you will feel a uniformly heated fluid or uniformly cold fluid moving, and the temperature will not change along the wide or along this direction. That we call it as the free stream temperature. Now, this T ambient indicates the free stream temperature of a fluid that is moving over this surface, and the surface has a temperature Ts such that this Ts is greater than the free stream temperature. The surface temperature is greater than the free stream temperature of the moving fluid. If that is the case, then we know from our experience that heat will be absorbed by this fluid. If it is as the opposite, just 1 minute. এই ক্লাসটা নিয়ে একটু ফোন করছি, আর 10-15 মিনিট ক্লাস নেবো নিয়ে ফোন করছি।
Sure. You spoke of like we have to go from a certain distance from the plate, and from there we will be experiencing that free stream temperature. So, what is the distance that we have to go? Is it up to the boundary layer, or is it below or above? Would you please mention that?
It is some distance that we call it as the boundary layer. It is a distance beyond which we do not feel any change, that is called a thermal boundary layer.
Achha.
The distance beyond which we do not feel, that is called that is beyond the thermal boundary layer. And the zone within which we feel this variation, that zone is inside a zone that we call it as the zone of thermal boundary layer. The distance will be beyond the thickness of the local thickness of the thermal boundary layer, and the distance within that we can feel it. Beyond that we do not feel it. There is another boundary layer that is known as the thermal boundary layer. That may be distinct from the hydrodynamic boundary layer that you may have come across in the fluid mechanics course.
Yes,
Now,
sir.
what we are talking of is the heat flux. We are interested to know the heat flux. Again, because if you know the heat flux and if you know how it is varying over the x and y, then you can find out the rate of heat transfer over the entire surface by integrating this thing over the area. Now, so our primary concern would be to know the heat flux. Now, this heat flux that we are accustomed to find out in a simple way as equal to some coefficient into delta t. That is, it is given as this heat flux is given as H into delta t is given as Ts minus T infinity. The surface temperature minus the free stream temperature, because they have unique values. Surface temperature has a unique value, free stream temperature has a unique value. Whereas we cannot take this temperature at in between points because there the temperature will vary. So we define a constant known as H, is called the convection coefficient constant, coefficient of convection. And accordingly, we define the convective heat flux as equal to some constant given by a symbol H into delta T is the temperature of the wall minus the free stream temperature. The convective heat flux is given by some coefficient known as the coefficient of convection multiplied by the temperature difference given by Tw minus T ambient or T free stream or ambient temperature. Whereas this is the wall temperature and this is the fluid temperature. And the overall temperature difference, the larger the difference, the more will be the heat flux. So this heat flux is proportional to this temperature difference, and the constant of proportionality is given by a constant known as the coefficient of heat transfer. And what is the unit of this thing? It will be equal to watt per meter square per Kelvin. Unit of this will be watt per meter square per Kelvin. Whereas the unit of conductivity will be watt per meter Kelvin. Here the unit of H will be watt per meter square Kelvin. Now the question is, it appears to be very simple compared to the situation of conduction. As such, it appears much simpler because the heat flux is given by a constant multiplied by the temperature difference. This is known. Now the question is, how do you know this value? What will be the value of this constant, the convection coefficient? That is the subject matter of study of the entire course on convection heat transfer. Now, we have to know what is the value of H in a given situation. As I said, this phenomenon that we are studying, the convection the heat transfer as a whole, it is the magnitudes we have to find out in a given situation. And what do we mean by this situation? Is a sum total of many things. One, the nature of the material that we are dealing with. By nature, we mean what are the properties of those materials, the geometry of the material, what is the thickness kind of thing. They are pertaining to the geometry of the body that we are talking of. Also, it depends on the externally imposed situation given by the temperature difference or this type of things. So, it appears much simple if we know the value of this thing. Now, how do you know the value of this thing? That I'll just elaborate within coming 3-4 minutes and then I'll stop. Now, what people do to find out these values? Normally, when we work out a problem, to begin with, we'll see that you may be given a question that if the value of H is this, and if you know the value of this is equal to this free stream temperature is known, what is the value of heat flux? Working out is very simple. The question is, who will tell me the value of this H? How do I know the value of H? How people find out the value of H? I am just introducing how people find out. Now, if you see this surface from where the heat is coming out and is going into the fluid, you see this thing. There is a surface that may be stationary and there is a fluid that is moving along the surface. Now, this movement may be along the surface if the fluid is being forced, it is a forced convection, or even if it is not a forced convection, even if you have a heated plate and that is in contact with a static, otherwise quiescent medium, even then, when you bring this medium in contact with a heated surface, then what will happen? This fluid will become heated, so it will become lighter, it will tend to move upward. And as it moves upward, fluid will come from the neighborhood, it will try to fill up that gap. So there will be a current produced that will be like this. Initially it will come in the horizontal direction, then it will move upward. So there will be a current like this. There will be a current like this. So that
Okay,
current,
so
as we have discussed, is known as a natural convection. So convection involves movement of the fluid that is in adjacent to the surface. And here it is a kind of a more or less horizontal movement. In that case, it will be predominantly vertically upward movement against the direction of gravity. Now, even though the fluid is moving because of convection, we are fortunate in one sense that even though the fluid as a whole is moving, there will be one layer of fluid that will be sticking on the wall. So even if it is a convecting fluid, at y is equal to 0, the fluid at y is equal to 0 plus, there will be a fluid particle that will be stationary because of a property known as, because of a phenomenon known as no slip phenomenon that arises due to viscosity of the fluid. If the fluid is a viscous one, then because of viscosity, a very thin layer, a very particular level of layer will be sticking on the wall. That layer cannot move. So, how, if we magnify that situation, we have a wall and we have a particle that is sitting on the, that is sticking to the wall, and there are other particles that are moving with respect to this, with relation to this fluid particle. There is another particle that is moving. There will be another particle that will be moving at a larger velocity. There will be another particle that will be moving with a still larger velocity. But the particle that is sitting on y is equal to 0 plus, that is not moving. So the only way the heat passes from the wall through that particle to the next layer of the particle is by conduction again. So to the sticking particle also the heat is flowing by conduction only. Even the bulk of the fluid is participating in the convective motion, but the fluid particle that is sticking on the wall, that is also participating in the heat transport process from the wall via that particle into the mainstream. That via that particle also the movement of heat is because of conduction. So what you can do is that we can apply the same law of heat conduction into that particle also. So the heat which is coming out of the wall, it passes through the intermediate particle, intermediate in between particle that is sitting on y is equal to 0 plus. There also the heat flow is along that y means the normal to the wall. The direction along the wall that I consider as x, and the direction normal to the wall that I consider as y. Now, because we are talking of a particle that is also sticking on the wall because of no slip phenomenon, because of viscosity, there also it is by conduction. We can apply the law of heat conduction even as minus k suffix f. We are highlighting this f to indicate that this property of conductivity pertains to the fluid conductivity. The conductivity of the fluid multiplied by the temperature gradient along y at evaluated at y is equal to 0 plus or evaluated at y equal to 0. So if we can evaluate this conductivity in the y direction, this temperature gradient in the y direction at y equal to 0 plus, then multiply that with the conductivity of the fluid with a minus sign, you get the heat flux. So you could find out the heat flux also through this thing. Now, question is how do you know the this temperature gradient? That is again something that is not known a priori. It is the job of the heat transfer people, the people who are involved in research, to find out the value of H under different situations. There are a large group of people who are working throughout the world for the last 100 years, more than that, that people are trying to find out the value of H under different situation. Once they document something, the value of H under a given situation, that becomes some kind of a useful thing for other people who will be using it in a simplistic way. So there will be one group of people who will be using this value, and there will be another group of people who are finding out these values and documenting them in the form of well laid down formulas. So the job of a scientist, the engineers, the researchers, their job is to find out the value of H under different situations. How do they find out? Is one way can be through a theoretical approach. That is, if you can equate these two, then what we can say is that if you can equate these two, we can say H is equal to minus K del T del Y at Y equal to 0 plus divided by this temperature difference between the wall and the free steam temperature. So for that, what we require to know is what is the temperature gradient. The conductivity of the fluid can be found out through some kind of experimental means. It may be also available in some handbook. It is a standard material. But to find out this thing, again, it involves a rigorous exercise. Now, this thing we can do it theoretically. This thing we can do it experimentally. This we will discuss in our next class.
Sir, would you please repeat why we are choosing KF and not KS?
Can you, because it is not clear, I cannot hear your question very clearly.
Sir, I am telling that why we are choosing KF and not KS.
Why?
We are choosing KF and not KS, sir. Is it clear, sir? Am I able? Wait, sir, I'm writing down my question.
You're right. I cannot actually. There is some kind of a echo type of thing is happening.
Yes, sir.
Can
Yeah.
you write what you are telling? Can you write it in a text box or something?
Sir, I have written it in the chat box, sir.
I'm just seeing what chat box.
Gmeet chat box, sir. Gmeet chat
Yeah, I'm
box.
just seeing. Why is it K not KS? You can do it if you are using del T del Y at if you are dealing with del T del Y at Y equal to 0 plus, then that means you are talking of the fluid domain. Then you take K. You can do it with del T del Y at Y equal to 0 minus, then you can use KS. So it depends which which domain you have the information. If you have the
Okay, sir.
part information about the fluid domain, then you can use the temperature gradient. Only when you have part knowledge, you can gather more knowledge. That is, if you have part knowledge about the fluid domain, you can gather more knowledge like del T del Y in the fluid domain. In that case, you know what is the fluid domain gradient given by del T del Y at Y equal to 0 plus. Then you have to use the K. But if you have the knowledge about the solid domain, not the fluid domain, then will be able to find out the del T del Y in the solid domain, which is given by del T del Y at Y equal to 0 minus. Then you can use the Ks. We'll show both the situation in two different contexts. And it is good that you have raised this question because many times we confuse between two such apparently very close to each other expression which are very similar. In one case, we have to consider the fluid property. In another case, we have to consider the solid property. So accordingly, we come up with two different numbers that we discuss. One is known as the Nusselt number, one is known as the Bayard number. This we have to be very careful about. We have to be conscious about what we are doing. Is there any other question? Otherwise, I'll just make a roll call and then try to stop.
Sir, I had written a question in the chat box.
So heat transfer due to convection of 0 plus would be same as the heat transfer due to convection at y equal to 0. No, this gradient will go on changing actually. So the gradient will go on changing, and this is the way to find out the heat transfer at the interface. Heat transfer at the interface, because we talk of when we talk of heat transfer, we have mentioned, if you remember, we discussed about the peculiarity of this particular form of energy transport, that we have tried to identify this as a kind of a boundary phenomenon. What is the boundary? That is as per our convenience. We choose a boundary at which we identify. Really, these are all conceptual things. What is our boundary? Is there any restriction that this will be our boundary? Nobody can impose any restriction on me. So what I take it as a boundary, accordingly at that boundary I try to identify what is the rate of heat transfer. And where I take my boundary, it depends on which one will be convenient for me. At the same time, it will lead you to an accurate result. Now, this is very important, that which way it is convenient. When you talk of a convection, if we know the surface temperature, so to identify the boundary at that surface is convenient for me. If I take if I take a boundary not at the surface, but at some distance away from the surface, inside the fluid, we do not know what is the surface condition there. We do not know the temperature at that surface. Okay. So if we take it at some point inside, we do not know what is the temperature there. We do not know what is the gradient there. In fact, what we know there in this type of problem is the surface temperature is known and the free stream temperature is known. Now, through some rigor, through some exercise, we have to calculate these things, the rate LOI value of this thing. That is the subject matter of experimental identification of gradient, or theoretically you have to find out the gradient. Because to find out the value of H, as we see, we refer to the temperature value on the boundary given by TW and the temperature gradient inside the domain. What will be that gradient? That gradient itself is to be worked out. And then you have to evaluate the temperature gradient at the wall, and then we can apply. Because we are interested to know what is the heat leaving the surface and going into the field. So for that, we have to evaluate the heat flow at the surface, at the interface between the solid and the fluid. For that, you have to take the gradient at the wall itself, not inside. Because the heat leaving the surface may not be equal to the heat leaving at some distance away. The heat which is leaving at Q equal to Y equal to 0 will not be equal to Q at Y equal to some distance away from the wall. So we have to evaluate everything on the wall, because we are interested to know what is the heat leaving the wall. Now, it means there is no restriction, just you have to consider fluid or solid property. I can follow this question.
No, sir. It is basically the response of what you have given to me when I asked for why KF not KS.
There is a restriction. Restriction is that if we can calculate the temperature gradient in the solid domain, then we can multiply that with the conductivity of the solid. If we can calculate the temperature gradient in the fluid domain, then we can multiply with the conductivity of the fluid. Now, where we can find out the temperature gradient, accordingly will be multiplied the conductivity of that part. Now, it is not that sometimes we may not be able to find out the gradient in the solid domain. Only way we can find out is the gradient in the fluid domain, then we'll be using that. If we can find out the gradient in the solid domain, then we can multiply. It depends where we have enough information to find out the requisite things. Okay, sometimes we may not have enough information in the solid domain, then we will not be able to do it. Then we will be forced to calculate the gradient in the fluid domain, and naturally then we have to multiply with the conductivity of the fluid. Sometimes there may be that we have knowledge only about the solid domain, we do not know the fluid domain, enough information, then we have to calculate the derivative, the temperature gradient in the solid domain. It depends where you have enough information to calculate the requisite. Everything may not be known everywhere. If many things are known everywhere, then you have freedom to choose according to your convenience. But sometimes maybe some part of information is available in the solid domain and whole information is available in the fluid domain. Then you use the fluid domain If you have all information in the solid domain, then you use the information for the solid domain like that. Maybe there are cases where information for both the solid domain and fluid domain, they are not simultaneously available. Then we have to stick to the domain where we have every information. If both are available, then you decide which one will be suitable for you, convenient for you. Accordingly, you adopt that thing. You follow? There may be. I'll show
Yes, sir.
you.
Yes, sir.
Yes,
I'll
sir.
show you a situation where you know full information about one domain only. Then there is no question of choosing the other domain. There may be cases where you have situation for both the domains. Okay.
Okay, sir. Thank you.
Like suppose that wall, if it is the surface of the wall,
Mm-hmm.
then what you know is the condition on the surface. Do you know anything inside the surface?
No.
So you don't have the information about the other edge of the surface.
Yes, sir.
Then above the surface, you may know what is the surface temperature, you know what is the free steam temperature. Suppose you are calculating the heat extraction from the surface to a fluid, then you know only the skin of the surface, you do not know what is underneath the surface. Then how do you work out on the basis of the conduction in the solid? You cannot. The other part of the surface is not accessible to you. Then you have to take the surface and the fluid in contact. But if you know every information about the surface, it is better to calculate this on the basis of the solid only, because the conduction phenomenon is much simpler, and the convection phenomenon is no match in terms of complexity. That complexity of convection is maybe 1,000 times more than the complexity of the conduction problem. Okay. Any other question? Otherwise, I'll make the roll call and then leave. Universe has done. Rishabh, roll 50.